I'd like to thank Logos Instituut for inviting me to address this conference. Today, I'm going to give the first of two talks, looking at the geological evidence for a worldwide flood. Tomorrow, I'm going to take a detailed look at a specific case study in flood geology research. But in this first talk, I want to give a somewhat broader perspective, perhaps addressing some familiar themes, but also including some material that hopefully will be new to you. I want to begin with this book, The Lost World of the Flood, which I recently read. It was published in 2018 and it's written by two well-known Bible scholars, Tremper Longman and John Walton. I was interested to hear what these two biblical scholars had to say about the scriptural narrative of the flood. As I read the book, one of the things that struck me most forcibly was the author's basic agreement with creationists that the Bible does describe a worldwide flood. For example, they say that the description given in the Bible truly is that of a worldwide flood, not a local flood. And they go on to say that, in spite of its good intentions and proper motivations, the attempt to interpret the biblical text as knowingly describing a local flood remains unconvincing. It's our conclusion, they say, that Genesis 6-8 describes a worldwide, not a local flood. Well, so far so good. But then their argument takes a rather curious turn, because although they acknowledge that the Bible describes the flood as a worldwide event, they say that this doesn't mean that the flood was in fact worldwide. We contend, they say, that employing universalistic rhetoric to portray the impact and significance of the flood as a cosmic cataclysm does not mean that the ancient Israelites or the author considered the physical scope or geographical range to be universal. Rather, they assert that hyperbole permeates the account of the flood, including the description of the wickedness of the pre-flood world, the dimensions of the ark, and the details of the flood itself. They conclude that Genesis 6-9 pertains to a local flood described rhetorically as a worldwide flood, to make a theological point. Now, I think we have to ask, what is leading these authors to draw such a counterintuitive conclusion? To be fair, they do present some arguments based on parallels with the conquest narratives in the book of Joshua and with other documents from the ancient Near East, but all of that seems pretty thin to me. What seems much clearer, not least because they emphasize it over and over again in their book, is that they don't think there's any geological evidence of a worldwide flood. They say, for example, the Bible describes a worldwide flood, yet absolutely no geological evidence supports a worldwide flood. And later they say there is absolutely no evidence for a worldwide flood, and there should be, if there was such an all-encompassing flood. Now, of course, they recognise that creationists take a different view, but they make it very plain that they reject what they describe as the desperate attempts of a handful of outlier scientists to argue to the contrary. So what to make of the lost world of the flood? In some ways, I think it marks a step forward in the flood debate because the authors are very clear that the biblical description is of a worldwide flood and that the local flood reading, which is very popular among evangelicals, is not consistent with the text of Scripture. But we also need to address the author's claim that there's no geological evidence of a worldwide flood, because their reinterpretation of the biblical text really does seem to hinge upon this. So I hope that for the next 40 minutes or so, you'll indulge this particular outlier scientist, desperate or not, as he seeks to explain why he thinks that Longman and Walton are simply wrong about the lack of geological evidence. I want to consider the geological evidence of a worldwide flood under three broad headings. Firstly, widespread, catastrophically deposited sedimentary strata. Secondly, large-scale soft sediment deformation features. And then thirdly, extensive high-elevation, low-relief erosional surfaces. Let's begin with the first of these and consider a few examples. The first example I want to look at is the Shinarump Conglomerate of the Colorado Plateau. The Shinarump Conglomerate is the lowermost member of the Upper Triassic Chinle Formation, and it's a remarkable sheet-like deposit that crops out extensively across northern Arizona and southern Utah, with less extensive exposures in other parts of Utah and across several other southwestern states. In some parts of the region, erosion has removed the Shinarump, and in other places it's buried in the subsurface. But it's thought that its original aerial extent would have exceeded 365,000 square kilometres. And yet, despite its enormous lateral extent, the Shinarump is quite thin, averaging at only about 15 to 30 metres thick. The conglomerate contains pebbles and cobbles of quartz, quartzite, and chert. Fragments of petrified wood, including some very large logs, are also locally abundant. The quartz and quartzite clasts don't match any nearby source, so it's thought that they must have been transported some considerable distance. In addition, much of the Shinarump is cross-bedded, indicating that it was deposited by fast-flowing water currents. So how was this remarkable rock unit formed? Conventional geologists suggest that the Shinarump was deposited by a complex network of braided streams, with the deposits of these streams ultimately coalescing to form this extensive blanket-like body of conglomerate. But there are problems with this interpretation. In central and eastern Utah and a few other places, the Shinarump can be seen to fill erosional channels and other topographic relief. But across most of its outcrop, there's no sign of the channel erosion that we'd expect, and the Shinarump sits on top of the underlying rocks with a very flat contact. In the modern world, there's no example of a thin conglomerate of such uniform thickness being deposited across such a broad area. It's hard to disagree with Gregory when he said in 1938 that the conditions under which the Shinarump was deposited are difficult to visualize. What conditions, he said, could be so persistent and so uniform as to permit the deposition of a thin sheet of material essentially alike over thousands of square miles in Utah, Arizona, and Nevada? The broad sheet-like geometry of the Shinarump and its relative uniformity over thousands of square kilometres, along with the evidence of long-distance transport and powerful water currents, makes deposition during the worldwide flood a viable mechanism for explaining this remarkable rock unit. The second example I want to look at is the Middle Ordovician St. Peter Sandstone of the mid-continental United States. Now, like the Shinarump, the St. Peter is relatively thin, averaging about 25 to 30 metres thick. But again, it has an enormous lateral extent. It stretches from Minnesota in the north to Arkansas in the south, and from Illinois in the east to Nebraska in the west. It's thought to cover about 650,000 square kilometres, mostly in the subsurface. When we look at the St. Peter under the microscope, we discover that it's composed of fine to medium-sized sand grains, generally quite well rounded and well sorted, and with frosted surfaces. The sand grains are almost exclusively quartz. The silica content is not usually less than 96%, and in some places it's 99% or higher, which means that the St. Peter has been highly prized by glassmakers. Most of the St. Peter sandstone is massive and homogeneous in appearance, with indistinct bedding in outcrop. However, some parts of the formation are clearly laminated or cross-bedded. In southern Wisconsin, sets of crossbeds up to 11 metres thick indicate that parts of the formation were deposited as very large sand dunes. So how was the St. Peter sandstone formed? The conventional view is that it was deposited in a shallow marine offshore environment associated with a slowly advancing ocean, perhaps reworking earlier coastal dune deposits. But again, there's no obvious modern equivalent of such a widespread blanket sandstone forming today. In fact, there are some striking differences between the St. Peter sandstone and the sands being deposited on modern shallow marine shelves. For example, the sands on the present-day Atlantic shelf average only 1.5 to 4.5 metres thick, and that's before burial and compaction. But the St. Peter sandstone averages about 30 metres thick. Given its remarkable purity, its sheet-like geometry, its wide aerial extent, and its location in the middle of the continent, transport and deposition of this sandstone during the worldwide flood seems to be a reasonable model. Now, I could go on multiplying examples, but I'll give you just one more. An extremely persistent Devonian shale, known as the Chattanooga in the eastern United States, but given a variety of local names elsewhere. Although it's less than 10 metres thick, this remarkable rock unit has been traced across at least 11 states, mostly in the subsurface, and it also occurs in Alberta in Canada. What's more, the shale is thought to be about the same age everywhere, suggesting near simultaneous deposition over a very broad part of the North American continent. The Chattanooga is what geologists call a black shale, and it gets its dark coloration from its high organic content, typically around 15 to 20%. Recently, there have been efforts to exploit the natural gas in the Chattanooga by fracking. However, the Chattanooga doesn't contain many macrofossils. Those that are found include some conodonts, brachiopods, and a few plants. So how was the Chattanooga Shale formed? One textbook says, reconstruction of the conditions under which the shale was deposited is difficult. On the one hand, the presence of erosional channels, silt layers, and the macrofossils that are found suggest deposition in shallow water. On the other hand, its fine layering, the restricted fossil fauna, and the high organic content suggests oxygen-poor conditions consistent with deeper water. Once again, there's no obvious modern equivalent of the Chattanooga Shale. In fact, black shales generally are quite enigmatic, and their origin is still much debated. The almost simultaneous deposition of such a remarkably extensive yet thin shale deposit across such a broad swathe of the North American continent seems consistent with the expectations of the flood model. Well, so far we've been focusing on the remarkable persistence of some individual rock units. But since the 1960s, geologists have recognised that sedimentary strata are grouped in packages or sequences, bounded below and above by regional erosional surfaces called unconformities. And the recognition of these sequences has revealed some astonishing global patterns. These unconformity-bound sequences were first discovered by professional geologists, mostly in the oil and gas industry. Careful field mapping, combined with data from well logs and seismic surveys, allowed these sequences to be recognised and then correlated both in outcrop and in the subsurface. The diagram on the right shows a typical sequence, with the sediments at the bottom deposited first and those at the top deposited last. The sequence begins with conglomerates and sandstones, which are followed by shales, and then by carbonates or limestones. There's a general decrease in the size of the sedimentary particles as you go up through the sequence, so that the coarsest sediments are at the bottom and the finest grained sediments at the top. Geologists call this a fining upwards sequence. In 1963, the geologist Lawrence Sloss identified 6 such megasequences across the North American continent. Here you can see the geological column on the left, with the Precambrian and Cambrian at the bottom, and the Tertiary and Quaternary at the top. The horizontal dimension represents a roughly west to east transect across the North American continent, with the mid-continent near the centre of the diagram. The black areas represent gaps in the stratigraphic record where no deposition of sediments was taking place. These are the erosional unconformities that mark the bottom and top of each sedimentary sequence. The orange and brown areas represent portions of the record where sediments were deposited. And you can see that there are 6 major sedimentary sequences separated from one another by regional unconformities. Lawrence Sloss gave each of these sedimentary sequences a name, which you can see on the left-hand side in the white typeface, the Sauk sequence, Tippecanoe sequence, and so on. Each of these megasequences can be traced across the North American continent. Consider the lowermost of the Sloss sequences, the Sauk sequence. In the Grand Canyon in Arizona, it's represented by 3 major rock units, the Tapeats Sandstone, the Bright Angel Shale, and the Muave limestone. Here's our fining upward sequence: sands, followed by shales, followed by limestones. The sandstones are thought to represent a time when the water was relatively shallow and the depositional energy was high. The shales, a time when the water was a bit deeper and the environment a bit less energetic. And the limestone, a time when the water was deepest and the depositional environment was the least energetic. Now, in 2018, Tim Clary and Davis Werner of the Institute for Creation Research published a significant paper in which they compiled more than 1,500 stratigraphic columns for 3 continents: North America, Central and South America, and Africa, using published outcrop data, data from boreholes and cores, cross-sections and seismic data. They also generated maps of distinctive rock types or distinctive rock units and noted where they were located within the stratigraphic columns. Here you can see their map of the Sauk sequence across North America, which reveals its extraordinary extent across the continent. The basal Sauk sandstone, shown in yellow, extends from the Mexico border in the south to Canada in the north, and from southern California and Nevada in the west to New England and Maine in the east. As we've already said, in Grand Canyon, this sandstone is known as the Tapete sandstone, but it's given a variety of local names elsewhere. However, they're basically lateral equivalents to one another, and they have similar characteristics wherever we find them. The geographical extent of this sandstone sheet is truly remarkable. But in fact, things are even more extraordinary than that, because the same stratigraphic sequence can be discerned not only across North America, but on other continents. Here are some local stratigraphic columns compiled by Andrew Snelling in 2015, showing the Sauk sandstone at several widely separated localities. On the far left, we have the Tapete sandstone of the Grand Canyon, where it rests on an eroded basement of older rocks. 2,000 kilometers away, in northwestern Wisconsin, we have essentially the same sandstone, referred to here as the Mount Simon sandstone, also resting on eroded bedrock and at the same level in the stratigraphic record. But then we move to Libya in North Africa, and we see a similar sandstone at the same level in the record. And on the right, another similar sandstone at Timna in southern Israel, again resting on the eroded bedrock, just like the Tapete sandstone in the Grand Canyon. So what do these extraordinary sedimentary sequences mean? Well, we have a global signature here, and that's exactly what we'd expect if a worldwide flood had taken place as the Bible describes. Conventional geologists interpret these megasequences as a record of the gradual rise and fall of sea level over timescales of millions of years, with successive episodes of flooding of the world's continents. But creation geologists see each of these megasequences as evidence of the catastrophic incursion of the ocean waters onto the continents during the flood, driven by rapid movements of the Earth's tectonic plates, and the global sedimentary sequences left behind as a powerful testimony to the worldwide events described in the book of Genesis. So we have widespread, catastrophically deposited sedimentary strata spanning the world's continents. But a second category of evidence for a worldwide flood concerns the large-scale soft sediment deformation features found in many thick sequences of sedimentary strata. And here we'll take a look at 2 particularly well-studied examples. Firstly, the sandstone pipes of Kodachrome Basin State Park in Utah, and secondly, the sandstone dikes of the Front Range of the Rocky Mountains in Colorado. Our first example concerns the sandstone pipes of Kodachrome Basin State Park in southern Utah. Kodachrome Basin covers an area of about 8 square kilometers, just a short distance to the east of the famous Bryce Canyon. The rocks in the park are flat-lying or gently dipping sedimentary strata of mostly Jurassic age. On the left, you can see the local stratigraphic column showing the Jurassic rocks belonging to the Carmel, Entrada, and Henryville formations. There are also some younger Cretaceous sediments and some unnamed conglomerates of Pliocene to Pleistocene age. But without doubt, the most intriguing feature of the park's geology are the large number of vertical sandstone columns or pipes that penetrate the surrounding country rocks. In 1985, Dwight Hornbacher reported mapping 67 of these curious features in and around the vicinity of Kodachrome Park. As a result of weathering and erosion, many of the pipes now stand out as isolated spires or towers, the tallest measuring 52 metres high and the widest 15 metres across. So how did these sandstone pipes originate? The evidence shows that the sand in the pipes came from the sedimentary layers below and was forcibly injected upwards into the overlying sediments. Some of the pipes are filled with homogeneous fine sand, but others, like this very large pipe known as Chimney Rock, contain bits of carbonised wood and fragments of the surrounding rocks brought up with the sand as it was injected upwards. The large mudstone fragment you can see in the photo on the right was sourced from rocks 100 metres below the level of the pipe. Some of the pipes even display flow structures and vertical scratch marks created at the time the sand was injected. So what caused the sand to be injected upwards into the overlying sediments? Hornbacher considered several possible mechanisms, most of which could be readily ruled out. The evidence favoured a seismic or earthquake origin. Earthquakes have the potential to fluidise sediments so that they can be remobilised and injected into the surrounding strata. But of course, for that to happen, the sand has to be soft and unconsolidated when the earthquake occurs. And here's where we run into a conundrum for the conventional geological model. There's general agreement that the sand in the pipes was sourced from the Paria River and Windsor members of the Carmel Formation. We also know from field observations that most of the pipes intrude the Gunsight Butte member of the Entrada Sandstone, and that at least one of them penetrates the Escalante member of the Entrada Sandstone. So geologists have argued that the sandstone pipes must have been in place after the Escalante member of the Entrada was laid down, perhaps at about the time the Henryville sandstone was being deposited. Now, given that the source beds for the sandstone pipes are conventionally dated to around 160 to 170 million years old, and that the Henryville sandstone is considered to be about 150 million years old, it would seem that in the conventional model, at least 10 million years must have passed between the time the sand was originally deposited and the time it was intruded into the overlying strata. But in fact, the problem may be even greater than that. Dwight Hornbacher found one sandstone pipe that was capped by a contorted conglomerate, and he observed fluid escape structures that seemed to extend from the sandstone pipe into the conglomerate. When he analysed the conglomerate in the laboratory, he found that it matched the conglomerates elsewhere in the park, and this, along with some other data, led him to conclude that the sandstone pipes must have been intruded sometime in the Pliocene or Pleistocene. He even identified a fault 10 kilometres to the west, which had been active during the Pliocene, and he argued that this would have provided sufficient energy for the injection of the sand. Now, if Hornbacher is right, then the time according to the conventional model between the sediments being deposited and being injected into the overlying strata is not 10 million years, but 150 million years. I think the problem is obvious. How could the sand have escaped lithification, in other words being hardened into rock, for all of that time? Sediments are readily lithified in the presence of mineral-bearing waters, especially when deeply buried. Geological evidence indicates that more than 1,200 metres of sediment once covered the area where the pipes are found, and given the known rates of increase of temperature and pressure with depth, this overburden would have readily induced lithification over such timescales. Nor does it seem very likely that the sediments were originally lithified and then the mineral cements subsequently dissolved before the injection event. The process of delithification rarely takes place at the same time over such a wide area and throughout such a thick sequence of varied sediments. And of course, we'd expect to see evidence of it in the sediments themselves. However, a model in which there was only a short time span between deposition of the sand and the subsequent seismic activity and intrusion of the pipes would match the data quite well. And the worldwide flood described in the Bible would have provided the circumstances in which thick sequences of strata could build up and be deformed over short timescales. Our second example presents an even greater challenge to the conventional model. To help you understand why, let me set the scene. Along the southeast margin of the Front Range of the Rocky Mountains in Colorado, there's a very abrupt change in elevation resulting from large vertical movements associated with reverse faults, including one very prominent northwest trending fault called the Ute Pass Fault. On the west side of the fault, there are outcrops of the Pikes Peak granite and some associated metamorphic rocks of late Precambrian age. They're shown in pink on the map on the left. All the younger sedimentary rocks have been stripped away on the west side by erosion. But on the east side of the fault, there are more than 5,000 metres of younger flat-lying sedimentary strata. On the right-hand side of the slide, you can see a cross-section of the Ute Pass Fault, showing how the reverse faulting has thrown up the block of granitic rocks to the west and downthrown the younger rocks to the east. Another of the remarkable features of Colorado's Front Range are the near-vertical sheets of sandstone enclosed within the Pikes Peak granite on the upthrown side of the fault. These sandstone dikes were first described in the late 1800s. They vary greatly in size, from a few centimetres thick to bodies almost 300 metres wide. On the left, you can see an example of a very small dike with a pen for scale, while on the right you can see the Christola dike, a 100-metre wide sandstone body that forms a prominent ridge near the town of Christola. So how were these sandstone dikes formed? Well, the evidence suggests that the sand was injected into the fractured granite while it was in a soft and unconsolidated state. The sand grains aren't broken, as they would be if they'd been cemented together before injection. And angular fragments of the granite are commonly enclosed within the sandstone, evidently caught up with the sand when it was injected. In some dikes, the included fragments show a preferred alignment and flow banding is evident. All of these features indicate the forceful fluidized injection of sand along fractures in the crystalline bedrock. Now, I should make a brief aside here to say that recently some geologists have sought to draw a distinction between the smaller sandstone dikes, which they agree were injected into the granite in a fluidized state, and the larger sandstone bodies such as the one at Christola, which they say were emplaced along faults as slabs of consolidated rock. However, the larger bodies have the same features as the smaller ones, suggesting that all of these sandstone bodies were in fact emplaced as dikes, as previous field investigators proposed. In 1965, the geologist John Harms mapped over 200 of the sandstone dikes along the southeastern margin of Colorado's Front Range, and he noted that they were strikingly uniform in appearance, consisting mostly of a medium-grained, poorly sorted quartz sandstone. He observed that the grain size, shape, and composition closely matched the Sauk sandstone of Upper Cambrian age, and he concluded that the sand in the dikes had been sourced from the Sauk. On the left, you can see an outcrop of the Sauk sandstone near Manitou Springs, where it sits on an eroded basement of Pikes Peak granite. So when were the sandstone dikes injected into the granite? John Harms argued that the injection event must have coincided with the main vertical displacement along the Front Range reverse faults. Several lines of evidence seem to point this way. Firstly, the dikes are mostly found within 1.5 kilometres of the faults. Secondly, the orientations of the dikes line up with the orientations of the reverse faults, especially in the case of the larger dikes. And thirdly, the dikes dip in the same direction as the reverse faults. So it seems there's an evident connection between the fault structures and the dikes. But here's where the conventional model runs into another time problem. The main episode of reverse faulting took place during the Laramide mountain building episode, or orogeny, which in the conventional model is dated to the late Cretaceous to Middle Eocene, about 70 to 50 million years ago. But the Sauk sandstone, which seems to be the source of the sand in the dikes, is dated to the Upper Cambrian, about 510 million years ago. In other words, 450 million years must have passed from when the sand was deposited to when it was injected into the granite. And again, we're faced with the question, how could the sand have remained unconsolidated for so long? At the time the dikes were injected, the Sauk sandstone was buried beneath 4,500 metres of younger strata. And given the temperatures and pressures at those depths, it would readily have become hardened into rock. So it's no wonder that the timing of emplacement has become a major point of controversy. As one group of geologists put it, Laramide movement in the late Cretaceous to early Tertiary would have found the Sauk formation completely indurated as a quartzite and an unlikely candidate for fluidization. And so a number of geologists, past and present, have tended to downplay the obvious field relationships and to suggest that the dikes were actually intruded in the Cambrian or Ordovician, much closer to the time of deposition, and perhaps involving not the Sauk sandstone, but a hypothetical sand source now preserved only in the intruded sand bodies. But there are a number of problems with this idea. First of all, there's no evidence of movements along the reverse faults in the Cambrian or Ordovician that would have been sufficient to open up wide fractures in the Pikes Peak granite, unlike the movements we know were associated with the later Laramide event. Moreover, some of the sandstone dikes contain red mudstone and siltstone fragments that seem to match the rocks of the Fountain Formation, which is Carboniferous to Permian in age. And field geologists have mapped one sandstone body on the east side of the Ute Pass Fault that actually intrudes the Fountain Formation. Given the younger age of the Fountain Formation, these observations are inconsistent with a Cambrian to Ordovician intrusion event. So it seems that features such as the sandstone pipes of Utah's Kodachrome Basin and the sandstone dikes of Colorado's Front Range are best explained by the deformation of thick sequences of strata, while at least some of those strata were in an unlithified or poorly consolidated state. A worldwide flood of the kind described in the Bible provides the circumstances in which such rapid accumulation and deformation of strata could take place. So we have widespread catastrophically deposited strata, and we have evidence that thick sequences of strata accumulated so rapidly that it was possible for them to be deformed before they'd been turned into rock. The final geological feature I want us to consider are the high elevation, low relief erosional surfaces found in many places around the world. To understand the significance of these features, we need to spend a moment or two thinking about conventional models of landscape development. In 1899, the geologist William Davis proposed his famous geomorphic cycle, in which the Earth's landscape is sculpted over vast periods of time by erosional processes that are broadly similar to those operating today. Davis's model begins with the uplift of the land to form a youthful, high elevation, low relief surface characterized by poor drainage. Immediately after uplift, streams begin to cut down into this surface, forming narrow, steep-sided valleys with wide, flat areas separating the streams. After a few million years of erosion, we reach a stage of maturity, with maximum topographic relief and deep, wide valleys with narrow divides. But as erosion continues, we eventually reach the stage of old age, where the surface has been worn down to form a low elevation plain close to sea level, with poor drainage and meandering streams. And the cycle begins all over again with a new episode of uplift. Now, Davis's model proved to be very popular and it was widely adopted. And although it's been criticised over the years and is no longer universally accepted, cyclical models of one kind or another still tend to dominate thinking in the discipline of geomorphology. The important point I want to note here is that according to these kinds of models, high elevation, low relief surfaces characterize the youthful stage of landscape evolution, and they're basically regarded as short-lived features that are very readily destroyed by only a few million years of erosion. In fact, so pervasive was this viewpoint that in 1954, the geomorphologist William Thornbury claimed that no topographic surface of any great geological age existed anywhere in the world unless it had been preserved by being buried under younger rocks and then exhumed later by erosion. According to Thornbury, most of the Earth's topographic features were no older than the Pleistocene, up to 2.6 million years old, and topography older than the Miocene, more than 23 million years old, was exceedingly rare. Well, it turns out that Thornbury was wrong. Thanks to the work of a number of researchers around the world over the last several decades, we now know that high elevation surfaces of low relief are actually widespread across many continents of the world, and they're often considered to be of very great antiquity. Consider, for example, the so-called Gondwana Surface, an extensive erosional surface found across much of Australia, South Africa, and South America, with smaller remnants in India, Europe, and the United States. It's probably also preserved under the ice in eastern Antarctica. This surface is called the Gondwana Surface because it's thought to have originated prior to the breakup of the Gondwanan supercontinent in the Jurassic and early Cretaceous, and it's therefore considered to be about 150 million years old. The Gondwana Surface was first identified by the South African geomorphologist Lester King in the 1950s, and here you can see his reconstruction of the Gondwana Surface across the southern continents. Since the 1950s, King's pioneering work has been developed and extended and sometimes challenged by many other geologists. For example, the ancient erosion surfaces of southern Africa have been mapped more recently by Timothy Partridge and Rodney Maud. And on the right, you can see the map they produced compared with Lester King's map from 1955 on the left. Despite some significant differences, a number of supposedly very ancient erosion surfaces are still recognised across the southern part of the continent. A great deal of work has also been done on Australian landscapes by the geomorphologists C.R. Twydale and Cliff Ollier, and they've documented many elevated erosional surfaces of great geological age across much of the continent. Among them are the so-called Knot Surface in the southern Gawler Ranges of southern Australia, which is said to have survived largely unchanged for about 70 million years, and the Summit Surface of the northern and central Flinders Ranges, which is also said to date back to the Cretaceous. In fact, some surfaces may be older still. Consider the high plains of Kangaroo Island, the southern Eyre Peninsula, and the Mount Lofty Ranges in southern Australia. This erosional surface extends over about 8,500 square kilometres, and multiple lines of geological evidence suggest that it's late Triassic in age. That's conventionally about 230 million years old. Now, these high elevation, low relief surfaces present some challenging questions concerning geological processes and the timescales over which they operate. For one thing, these widespread elevated plains are not being formed by modern erosional processes, And in fact, it's hard to even imagine a slow and gradual erosional process that could have formed them. Another problem is explaining their survival to the present day. We know that many of these surfaces were not buried and then exhumed, as Thornbury suggested, but were instead exposed at the Earth's surface for almost the whole of their history. Twydale expressed the problem in these words. He said, "Even if it's accepted that estimates of the contemporary rate of degradation of land surfaces are several orders too high to provide an accurate yardstick of erosion in the geological past, there has surely been ample time for the very ancient features preserved in the present landscape to have been eradicated several times over." It's no wonder that he concluded that the survival of these paleoforms is in some degree an embarrassment to all of the commonly accepted models of landscape development. However, the worldwide flood described in the Bible provides an explanation for these otherwise enigmatic landforms. During the flood, the ocean waters would have covered the land, and the elevated land surfaces would have been exposed to extensive sheet-like erosion, especially as the flood waters retreated back into the ocean basins. Moreover, a recent worldwide flood explains how these landforms managed to survive to the present day. In the conventional model, these elevated surfaces must have been exposed to weathering and erosion for tens of millions of years, but in the flood model, they formed only thousands of years ago, and so their survival is much easier to explain. So to sum up, far from there being no geological evidence of a worldwide flood, we've seen in this talk that there is in fact a good deal of evidence that seems consistent with a worldwide flood, including widespread catastrophically deposited sedimentary strata, large-scale soft sediment deformation features, and extensive high-elevation, low-relief erosional surfaces. It seems clear to me that Longman and Walton's statements about the absence of geological evidence are at best too pessimistic and at worst fundamentally mistaken. Given the geological phenomena that we've considered here, we have to be open to the possibility that the Bible describes the flood as a worldwide event precisely because it was a worldwide event, and that there is geological evidence to confirm it. Now, of course, that doesn't mean that there aren't challenges to the flood geology model that need to be addressed, and we do have to take such challenges seriously. We recognise that not all of the data will be easy to explain, whatever model of Earth history we adopt. And in that spirit, in my next talk, I want to look in detail at one such challenge: the claim that flood geology is falsified by the existence of desert-deposited sandstones within the flood-deposited part of the stratigraphic record. I want to thank Dr. John Whitmore, Zachary Klein, the Institute for Creation Research, and Bill Hosch for kindly allowing me to include some of their photographs and diagrams in this talk.